Oh, yeah. So here it is, the package from PCBWay. It actually came a day early. It was estimated to be here Tuesday, and it is now Monday. Oh man, this is like better than Christmas. Oh yeah. Oh yeah. Oh my god, look at them. Oh man, that's awesome. Holy shit. That's so cool. It's just a stack of them. Alright, here it is. All the components are laid out. Look at that. Glorious, I say. Look at that beauty, huh? Look at that. Oh my. We got our buttons. And they all work. So that means all the resistors are good, all the switches are good, and all that's good. That's good, that's good, that's good. Alright. I'm impressed. Everything works, and it's just, it's so cool. I finally have something I can hold in my hand. Oh, this is amazing. But anyway, if you're still interested, this is my alpha prototype so far. I still have to work on the case a little bit, but I actually have circuit boards, which is cool. So I actually have a thing. It looks like a thing now. You could look at that and see what it is. As of right now, this version 1 should work fine for its intended purpose. I ordered a logic analyzer so that I can actually see what's going on with manual vehicles and older stuff and all that. So if it is just a different baud rate and I can just put in a different number and it works, then that's awesome, and I'll start sending these out. These will be great for manuals. But for automatics, I still want to do some more work. I want to see how hard it is to read the automatic transmission, because then we'll get speed. You can see what gear you're in. You can see what the solenoids are doing. I think the more exciting thing about speed is then I can try and calculate miles per gallon, which that's honestly my end goal. If I can see how many MPGs I'm getting live from the Jeep, then I've accomplished what I want to. So if you only care about the engine right now, then these will work fine. But if you want to see some other features, then I'd still have some more work to do to the boards. But yeah, that's where we're at right now. So for all you alpha testers out there, I've made a list and I've checked it twice, and I've got quite a few pretty good candidates out there. I'm impressed with how many people are willing to help, so that's awesome. Thumbs up to you guys. But once I figure out what's going on with the case, I can technically start populating these boards and sending them out. But again, I kind of want to add that auto transmission stuff. If it's easy and I can just do some quick little stuff to bodge it all together and fit it in the case, and that's great. But if it's more complicated, that it's going to take another board redesign, then maybe I'll ask you guys if you're willing to, if you just want to try out this version, or if you want to wait until I figure out what's going on with that. So again, for if you only got a manual transmission, then this is going to do everything you need. Along with the name, I've been thinking about clarifying it a little bit. Either calling it Renduinix engine monitor, or maybe just Renix engine monitor, and call the software Renduinix, just to help alleviate some confusion. A few people have asked about if it reads codes or if it does tuning and stuff like that, and I don't know if you can really tune these ECUs. It's got an RX pin, but I have no idea what you could send to it, and I kind of doubt it's reprogrammable. But yeah, I feel like calling it an engine monitor gives you a pretty clear idea of what it does. It monitors the engine. Another thing, the buttons kind of blend into the case, so I'm wondering if maybe I should change the color. There's a couple other button colors I can choose, so along with black, I could also do white or maybe red. So I don't know, maybe I could do white on the regulars and red on the home, or red on all of them and white on the home, or I don't know, something like that. But anyway, enough blabbering about progress so far. If you guys would like to make your own really basic version, I'm trying to keep this open source, so I'm sharing all my secrets, and I'm going to make sure that the board is open as well, so that way maybe I'll make it so if you want to add your own stuff in here, like your own sensors, or you want to do your own programming or things like that, that I'll make it more, hacker friendly, to have a base plate that other people can expand from. But yeah, if you're interested in, just seeing if the code works on your vehicle, see what you can read, or, if you want to start designing your own something or other, I'm going to show you guys how to, put together your own little Arduino and, just show you around the basics of the code and how everything works. All right, to the Jeep. Now then, let's get on to the exciting part. So, you want to build your own, huh? You would like to look into the mind of your Renix era Jeep, see what's going on, or, if you have a different version like some Volvos and Renaults and other strange, I think they're European cars. If you have yourselves a Renix, you'll be looking for this. Right over here. So generally, there might be a cover on this. On the Jeeps, there's like a big black cover here, but you'll see these two yellow things. So these are the pins you're after. So if you have these guys on your Jeep or other Renix era vehicle, then you're in the money. So if you notice, they're not all filled in, as they're not all useful. A lot of them have to do with ABS and things like that, and trans. But the first thing you got to decide is how you want to interface with it. You can just take, bare wire and just, fold it in half and stick it in there if you just want to do some quick testing, and that works great. But if you ever fuck up and the wires slip or something, you might short something out, and I blew up a transistor once doing that. So yeah, it's time to go up to the big boy toys. So you can buy the Molex connectors online. They're literally 50 cents a piece off DigiKey, and I'll give you the link for the female, male connectors, the pins, and all that. But just for the ECU, you only need 3 pins. You technically only need 2, but if you want to power the device off the vehicle, you'll need a third one for positive. So literally we just have the TX pin, the positive ignition, and the ground. And that just pops on there, like so. Alright. Okay, so here are the diagnostic connectors right here. So you notice we have a smaller one, D1, and a bigger one, D2. So you will find these on all models, and the pins should be the same. So if we come down here, at least for the Jeeps, on the 87 to 88 models, you can see the connectors for D1 and D2. A lot of them aren't used. Number 15 down here, this is for automatic transmission. Diagnosis, you got a couple other things, but the one we care about is number 1, ECU output TX, and that's the same on the newer ones. It's the same. A lot of them are the same too. And there's also RX data, so you can send data to this thing to make it do stuff. I have not gotten quite that advanced yet. And then you got other things, like ignition and latch relay and grounds and heaters and all kinds of stuff. But we don't really care about any of that. So if we come up, we want this one right here. Number 1. That is our TX output from the ECU. And then after that, number 4, if we come down here, that's ignition positive. So if you need power, you get that. And then number 7 is ignition ground, so you can use number 7 here. Or if you want to come over here, number 3 is also a ground. And I think there's another ground too, number 8. 8's a ground. There's all kinds of grounds, so whatever you need. But that's what you want. You need TX and you need a ground. Alright, so now we need to understand how the ECU outputs data. On the ECU pin, the TX pin, it's not just the straight pin, it's actually hooked up to a transistor. So I actually made I was able to make a fake output that mimics the ECU. So the way this works is that the ECU, just pretend this is the ECU from the Jeep. The TX pin, I don't know if it's connected to a resistor, if that's even necessary, but I just did that for safety. It's connected to an NPN transistor, and it has what's called an open collector output. On the transistor, you have a base, a collector, and an emitter. So what happens is when it sends data, it's either high or low. It comes out in binary. That's how computers talk to each other. You either get on or off. So what this is doing is when this turns on, it flows out of the emitter straight to ground. And what that does is by running current through the base, it's opening the collector, and that allows the collector to flow into ground. So this is an open collector output. So that means that when this is sending data and this is high, the RX pin, your receiver to your Arduino or your scanner, whatever the hell you want, that is going low because it's getting a path straight to ground. So the nice thing about this is if you send too much voltage or something like that and you blow this up, you will only break the transistor and the computer will be fine. But this also does allow for other voltages. So say this is a 5-volt system, you could run it on 3.3 or 1.5 or 9 or 12 or whatever you want. There's a lot of different voltage ranges that you could use, which is nice. This makes this a lot more expandable. When this is on and you get your path to ground, that's great. So you're getting a 0-volt signal. But when there's no signal, when this is low, the transistor isn't flowing anywhere, so the collector, it's not connected, it's floating, and that's not good. Whatever you're communicating with won't know what it is. It might be a little low or a little high, or it might be triggering, it might do all kinds of stuff, so you never want floating pins. So now we will go back to the system here. So this is from Phil Andrews. All right, he was the smart genius that figured all this out. I was just lucky enough to find, I dug up enough of his stuff online to actually put it all together. So he is the reason I am where I am right now. So big thanks for him. I can't fully explain, transistors still kind of boggle me with the biasing voltages and all that shit. They're a lot more complicated. You can kind of think of them as relays, but they vary and they can amplify and do all kinds of crazy shit. And there's a lot of math and confusing shit behind that, so I'm still a little lost there. There's two problems that we have to address here. The first problem is the floating pin. And all you got to do for that is add what's called a pull-up resistor. So I don't know if both of these are pull-up resistors or how this all works, but basically if there's no signal, what's happening is this resistor is just limiting the resistance, but it's bringing it up to 5 volts, so that way there's always a reference. So by adding a pull-up resistor, you get 5 volts when it's open, and then when it's closed, it'll go to ground instead and read 0 volts. So now we have a definite high or a definite low. So that's part one. Part two is the fact that since the signal is coming out of a transistor, it's effectively inverted. So when the ECU is outputting something that's high, it's going to ground, which means that the output signal is low. And when the ECU is not transmitting, then the pull-up resistor is bringing it high when the ECU is low. So what we have to do is reverse it, and that's what this transistor is for. So any generic NPN transistor will do the job. So by taking the output from the first transistor in the computer and putting it through another transistor, and I think adding another pull-up resistor, I'm not sure which one does which or how the hell that works, but by doing that, now it's effectively reversed, and when the ECU goes high, the Arduino goes high, and when the ECU goes low, the Arduino will go low. So, it works. If you got a better way to do this, and hey, let me know. I don't know a whole lot about this whole circuitry stuff, but it works. So let's see what that looks like on a breadboard. Okay, so I got everything hooked up on a breadboard just so you can see what it all looks like. So I took this diagram and I just put it into a breadboard. So in case you don't know how breadboards work, they're combined into rows. So we have a ground rail. It's a common ground rail that it goes across the entire bottom of the board and the top of the board. And you also have a positive rail that sits right next to it, and you can tell by the red and blue lines. So along with the power rails, you also have, like, each one of these rows is connected. So up and down, this row is all one line. This row is all one line. This row is all one line, and so forth. Okay, so try to ignore all the stuff up here and just worry about the stuff down here. So this is the whole connection that we need. We'll start at the transistor. So this right here is a simple NPN transistor. Now I'm using a... this is actually a pack that my dad had back when he used to mess with electronics, and they still work. Okay, so here's the one that I use. It's an F2N3904 EBC. I don't know if the EBC is important, but it's literally just a generic NPN transistor. And you can use just about anything. Phil used like a different kind, and that still works. Okay, so we'll start on the left. On the left leg is the emitter. The middle leg is the base, and the right leg is the collector. So if you come in here, you can see the transistor has a notch in it. So it's flat on one side and round on the other. So that's how you can tell. So when you look on it, the collector is always on the right if you're looking at the flat. At least for this version. You might have to check out the data sheet if you use something else. On the left, the emitter, the leftmost leg, you notice that runs into this gray line here, this guy, and that goes into the ground rail. So the emitter is being connected directly to ground. And the positive and ground rails are just connected to the Arduino. So you can see we have a ground. We have actually 2 grounds here, and we have a 5 volt. You want the 5 volt, not the 3.3. So we have those connected over here so that we can just access them easier. So next on the list is the base. Now the base has a resistor on it. That is our 3.3K resistor, and that is going from the positive rail straight to the base. And if we move over, the 1K is also going from the positive rail to the collector. Okay? But anyway, along with the base is where we get our signal. So this yellow wire over here that's connected to the base, this runs over to the TX pin of the Jeep. So if your connector's looking like this is our TX pin. This is what the ECU is outputting. So that runs over here to our base, and then we get to do magic from that. Now, on the collector side is this orange wire that runs over to our RX pin on the Arduino. Okay, so we got yellow wire is ECU in, orange wire is transistor out to the Arduino. Then we get our 2 resistors, we got our ground, and our commons. And then all we got to do in order to complete the loop is to attach our vehicle ground over here, which is this black wire on pin 7, over to our ground rail. So even though these are different voltages, the Arduino works off of a 5 volt and your vehicle is 12 to 14, you can still connect the grounds. We're not connecting the positives, just the grounds. And by doing that, the signals can go back and forth, but they don't interfere with each other, which is kind of interesting. So that's it. That's the whole thing right there. And then when you turn the car on, you should start receiving things on the RX pin. I guess I should add one more thing. If you want to run this off of the vehicle's power, like I was talking before, you're going to take pin 4, which is the ignition, and run it into the VIN pin, or the voltage in. So that is taking the raw voltage and regulating it. Do not connect this to your 5 volt. If you connect this to your 5 volt rail, you're going to blow everything up. And you don't want to do that, because the 5 volt bypasses the regulator, because you figure it's just, that's what is the 5 volts. So if you put any bigger voltage in there, you're not going to have a good day. So make sure that if you do use the vehicle power, it is going through a regulated pin, such as voltage in, or you could plug it into the power port over here if you have an adapter or something like that. So just be aware. But if you do it this way, then you don't even need a computer to power it. You can power it right off the vehicle. Alright, so now we're going to look into the Arduino part. The Arduinos are pretty simple little devices. They're built to try and help people out as much as possible. A lot of the hard work is done. The heart of most Arduinos is an Atmel processor. So it's this big chip here on the bigger guys. On smaller ones like this, it's literally that little chip in the middle. That's an Atmel processor as well. So that's what holds the code and does all the work and all that crap. And then everything else is just how it's laid out and connected. And then you have Arduino software, the IDE, the whatever the hell it is, the interface that talks to this and uploads the code and makes it real simple. If you've never done Arduino projects before, get an Arduino Uno. All right, start out with an Uno, because every single other board I've gone to, it takes something different to get it running. So the Uno's got the most support. Just start with something simple, and then if you want to work your way up, you can. Okay, so here's one of the problems I've been running into, and it's always hard to tell what's going on. Now, when you use the hardware serial lines, the RX and TX lines 0, 1, and 2, those are also connected to the USB chip or whatever, however it communicates them. So when you upload code, you'll notice that the TX and RX lights blink because there's data physically running through those lines. So if you also have things connected to that line, sometimes it might interfere with what's going on, and that's happening here. So I've always found that if I have to upload code, I have to pull this line. So if we pull off the RX line, then we won't get this error anymore, because I always get this compiling error that there's an error uploading to the sketch. But now if we pull that and then we hit upload, it'll go through and it accepts it and it works. So yeah, so now the code uploaded. So I don't know why, but that's just an issue with this. A little weird, but whatever. Okay, so now that you have your connection, you need to figure out what you're looking at. So the way that the Jeep outputs data, it's actually really simple. All it does is it outputs a string in a continuous loop over and over and over again at something called a baud rate. Now, this is I think it's considered a UART. There's no timing signal. So literally, the timing is the length that the bit stays either on or off. So there's no secondary clock signal or anything like that. It's literally just you have one line, one TX pin, that's it. And that's where all your information is. So what it does is the start byte is 0. So when it's in idle, it's all high. So these are all ones. So you get a big, gigantic, high signal. And then when it's ready to start, what it does is it drops it low for a byte, and then it starts reading them in. So right now, this recorded set right here is a string of 31, and this is for the 4.0 liter Jeeps. For different vehicles and engines, these will be different. But this is what the 31 string looks like. I've also seen a 32, which for some reason now when I shut my vehicle off, I'm getting a 32 for some reason. I also saw 36, and when that happens, they start to get out of order a little bit. Usually something gets shifted down just one, but that throws everything off. So yeah, it's something I have to look into. But if you just get the standard 31, then you can do that. Now the way you get this, I can show you how Phil's code works, so you can actually get the raw data input and see, just the regular stuff for yourself. But you just do a simple, like a serial dump. You just tell it to read in the incoming byte and then either print it or, do whatever the hell you want with it. And you just do that in a loop. And he uses putty, so I'll show you the computer part a little later, but it just dumps everything, and you can go in and read it. So we start at byte 0. Everything is 0 indexed here. We never start at 1. That's just how the code stuff works. So we have 31 total bytes, and each thing represents something. So if we come in a little closer, after our start byte, I have this string right here. We have the binary, which is converted into hex, which is a lot smaller. It's still the same stuff. And it's also converted into regular numbers, the decimal system that we're used to reading. So this is the off. This is what it looks like when the vehicle's off, and this is what it looks like when it's running. So if we work our way down the list, the first, second, and third bytes have to do with the prom number. I don't know. I'm sure they mean something, but I don't know what. But usually they don't change. Number 3, that's your map sensor. And then over here, I've got some math to figure that out. So the number that we get is divided by 51.2, and that'll equal our volts, 0 to 5 volts. Or we can convert it over here to inches of mercury. So we'll divide it by 9.13, and then add 3.1 as the base. So then our readings would be anywhere from 3.1 to 31 inches of mercury. And such as that. So the next two, we have our water, our coolant temperature sender in the block of the engine, and our intake air temperature sender. And if you want to convert it to Fahrenheit, it's real simple, so you got the math there. Next up is the battery voltage that the ECU reads. For some reason on mine, when the vehicle is off, it reads 0 as the battery voltage. And I'll have to check and see if it's on for a second or two and then shuts off when the fuel pump stops priming. But that's just kind of a glitch. That's just how mine works. Yours might display all the time, but mine only displays a reading when it's off. Next up is the oxygen sensor, and that's just converted to volts over here. So you divide it by 51.2, which is 0 to almost 5 volts. So that's that. Now the RPM. This one I had a lot of trouble trying to figure this out. Alright, it's got, if you see byte 8 is the low byte and byte 9 is the high byte. Now, all these readings are usually 1 byte, okay, which is 8 bits. So usually, 8-bit, 1 byte, and that's just the standard. Now this one, I guess in order to get more detail, they made this a 16-bit or a 2-byte number. So what you're doing is you're taking... Instead of reading in 8, you're reading in 16. So what you're doing is you're taking this byte right here and just putting it in front. So you're reading this one and you're reading that one. And by combining them into 16 bits in a row, you convert that into a decimal number. Okay, so here's an example that I have in the sketch right here. So what it's doing is, say for instance that byte 9 is 128, which is just, the middle, and 8 is 128. In decimal, it would look like this, but that's not really what we're doing. But in binary, it would be this and this. So it's a 16-bit word. which is just, it's 16 bits, it's 2 bytes. So what happens is you take this whole number here and you convert that into decimal and you get this number. So you get 32,000. So obviously this is much different than this. So that was the hardest part that I had is figuring that out, is that it's a 16-bit thing. So this is the number that we get, and then we convert this into what we need to. So you take that number right here, all right, and you divide it into this. So I found out it was 19,850,000 divided by that 16-bit number, and that'll equal your RPM. Now, obviously, it's never going to be this high. It'll usually be somewhere between, whatever. But that's how that happens. For 4 cylinders, it may be different. It might not. I'll have to look, but that's how it works for the Jeep 6-cylinder. All right, so then we get a couple more digits of the prom number. After that, we get our TPS. So this will give you either voltage if you want, or a percentage. Our spark advance, that is the ignition timing before top dead center. This is just a raw number. So the number that gets converted here into decimal is that's the number. There's no math required. So it would be 0 to 255, and that's the degrees before top dead center. Now some of these I don't know what they do. Some of them don't do anything, and some of them I'm not sure. So for instance, right here, byte 14 is always 0. It never changes. So that's probably just an unused byte. Next up is 15. Now this one does change between off and running, and it does some stuff, but I don't know what it does. It doesn't come up on the snap-on scanner, or if it does, I'll have to change the stream length and mess around with it, but there's a couple I don't know. All right, next up we have our barometric pressure reading, and all that this number is it reads the map sensor before you start it, and it saves that number. So like right here, 248, it came down and saved it as 248. So that was just the start reading. And that way I guess it saves this so it can do math or, whatever, do comparisons. Next up is another one, which I don't know what it does, but there is data. Next up, this one is interesting because on the snap-on scanner, it's two different things. So you have your loop state, so you have open loop, closed loop, or decel, which is, a different type. And you also have the exhaust, which is rich or lean. So this is where things get interesting and complicated. So what we're doing is we're taking the number and dividing it by 2, and if it's odd, it's equal to decel. If it's not odd and we get an even number out of this, then we have to do more. So we'd come over here and we take this number and we divide it by 64. If this number is then odd, it's closed loop. If it's even, then it's open loop. So it's a repeating pattern over and over and over again. It's very strange, but by doing that you can kind of figure it out. And then over here, if we want to figure out if it's rich or lean, this is a little more simple. If the number is less than 128, if it's lean. If it's greater than 127, it's rich. So that's not too bad. Next up is our injector pulse width. So this shows how long the injector is open for. And we just take that number divided by 7.81, and it's anywhere from 0 to 32 milliseconds. Number 20 is another thing that has no data, so who knows what that does. Number 21, this is a throttle switch or fuel sync. I never did the math for throttle switch. I really don't know what that is. I'll have to look into that. But the fuel sync is pretty simple. You divide it by 4. If it's odd, then it's negative. If it's even, it's positive. So it's something to do with the distributor. Next up, number 22, we get information, but I don't know what it is. Same for 23, I don't know. Next up, number 24, this is our short-term fuel trim. This is just a raw number, 0 to 255. If it's in the middle, it's good. If it's lower, then it's pulling fuel. If it's higher, it's adding more fuel. Number 25 does something. I don't know what, but it does something. 26 is our long-term fuel trim, so it's the same thing, 0 to 25. Next up is our knock sensor. That is just raw, 0 to 255. So if it's at 0, there's no knocking. If it's 255, is a lot. Next up, got another thing. This doesn't really change. Maybe this is like a running thing. So when it's at 255, it's off, and when it runs, it switches to 128. So maybe that's just telling you if the engine's running or not. I don't know. After that, we have our AC switch and request. So over here, if you divide it by 32, it's odd. It'll be on. Or if it's even, it's off. And then over here, if you divide it by 64, yes, that AC is being requested, and no if it's not. And then after that, number 30 is some more of the prom number, and then you have the stop bit. So there you go. That's the whole stream that's coming out of the Jeep, and that's all the math that we do to get the information that we do. So now that we have that, let's look into the code and see how it organizes everything into usable information. Okay, so I'm using my my Pro Trinket Arduino as a fake ECU output, so it just loops the stream, and it's got a counter variable in a couple of them, so that way, you know, things increase and we can actually see something happen. So I have this guy hooked up as it would be to our test adapter that runs off over here to this board, and this board's hooked up to the Uno. So the Uno is running Phil's original code. So we're going to plug that into the computer and see what we get here. So we're going to open a program called Putty. It's P-U-T-T-Y, and I think the T-Y or the T-T-Y, yeah, it's all capital. Okay, so this is what we want to change. I already have a default set here, so we're going to load that, but I'll show you what it looks like. You'll have to figure out what COM port your Arduino connects to. So when you figure out the COM port, you type it in here. Now the speed over here is going to be 62,500. Now what that means is that's the baud rate that the ECU communicates at. So that's how fast, you know, the data is coming out. This number might be different on manual vehicles. I'm not sure. I need to find someone with an oscilloscope, or I need to make a logic analyzer, or just suck it up and buy one. But I need to figure out what's going on because this doesn't work on every vehicle. But if you get an automatic, this should work. And then the connection type should be set to serial. Alright, so we get serial, we get the speed, we're all set up. So we're going to take our Arduino and we plug it in very gently now. Now the way I have this wired up, both of them are powered from the same one, so that's cool. We get the blinky lights, that's good. Alright, so we're going to load this, and we're going to hit open. So Phil Andrews code, this is version 0.2. So now what you're seeing is a big old mess of what the hell. So what this code does is it loops, and it looks for three things. It looks for the stop byte, the start byte, and then the only other condition is that the next byte after that is not 0. Because he had an issue where if the vehicle was off, that pattern would show up elsewhere, that he'd have a 0 and a 1, or a 0 and a 255 or whatever, so he just put that in. Now in my code, I have it set to look for the program number, because that's a lot more accurate and shouldn't change, and you should always be able to find the beginning. But yeah, so this is what it looks like when it's coming out of the computer. So I'm going to unplug this just so we can pause and take a look. So what we have here, if we expand this, you can see all the numbers. So the way his code works is it finds, you know, the start, and then it goes like this. So our first number is 177, that's the first part of the prom, then we get 20, and then we get 63, and then we start getting data. Alright, so everything looks good. Now if you had to figure this out on your own, what you would do is look through and find, you know, a 255, and then a 0, and then for me, since my program number is 177, that would be the third number I look for. So when I do like a raw dump, that's just, you know, the thing I'm looking for. But yeah, this right here is his debug code, and it just, you know, spells everything out and just shows you, breaks it into the bytes, the hexadecimal, and then the decimal. Okay, so now let's see what the second part of the code looks like since I uncommented it. Alright. So that part looks good. And look at that. So if you notice, the coolant temp sensor is one of the things that it adds. So you can actually watch the things go and do their stuff. So that's pretty neat. And you can see the time that Sketch has been running and all kinds of stuff like that. So that was just his little program that he wrote so that he could read what it was doing. Now I actually took it a step further and, you know, started working on stuff that interfaces with an LCD screen and stuff like this. Now his calculations are wrong for what mine would be. They're all off, but, you know, you get the idea. So there's a couple different things you can do with the computer, and, you know, you can also run it off an LCD. Alright, so now that we got that, I'll take you through how the code works, and you should be set. Okay, so now we can get into the nitty-gritty of how this thing actually works. So if you're familiar with Arduino code, then this might make sense to you. If not, well, you're in for a wild ride. Okay, so just in case you don't know what you're looking at all, I will spell it out as best I can. So first off, we'll start at the top over here. So the stuff that's in light gray is just comments, so that means that you can type words and the code ignores this, so it doesn't, you can write whatever the hell you want. So this right here is Renix version 0.3. This was made by Phil Andrews, and I guess Kez helped him out. So this is what got me started. I was able to find it on some Russian site. He used to host it on his server, but the server goes down after like a month or two, so what happened? Alright, so he likes to use unit 8, which this is just a byte, basically. It's just 8, from what I understand. And you declare some variables. Now, variables are things that are going to change in the code, so what you do is you give them a name so that they're a little more friendly. And you can also set them to things. So if we start at the top, right now our first byte that we declare as a variable will be prev, or preview, or previous, I guess. This is hex, FF, which if you convert it into decimal is 255. So he's setting this to, the max, which would be high. Setting this to max, setting that to max. Then we got position, which is set to 0. Right here, I believe this is an array. So we have a data stream array and an average stream array, and it's got 32 spots in it. So this is what we're going to use to put all the data in. And then we have the loop. The loop is just initially set to 0. And then after that, we got some more variables declared, which he used regular byte as well, unless this is what, I don't know. This is what happens when a bunch of people start working on the same code. Everyone codes differently. So he's got a bunch of different bytes, and then he's got a couple integers, and some unsigned, so these are bigger, and then we got some floats if you want decimal points, and some crap like that. So whatever, this just initially sets up the variables so that when you write your code, it's easier to read. Alright, so now we come into the setup part of the code. The first thing right off the bat is serial.begin 62,500. So this begins our serial comms at the speed that he found, so he used an oscilloscope to figure out how long the bit width was, and well, yeah, so there you go. So we start that, and now it knows what speed to communicate at. So now we're doing some pin modes. This sets some of the pins as inputs or outputs. 0 is the RX on the UART. I don't know if you have to set it to an input, but he does. And a very common thing that people do is set pin 13 to an output. It's connected to the LED on the board, so you can show, when things blink, you know that your code is doing something. So then right off the bat, after that, he does a digital write, and then what that means is it takes the pin and it digitally writes it whatever you tell it. So these are called arguments. The first argument is what pin do you want to write to, that is pin 13, and you could also set that to a variable. So if you wanted to come up here, you could do LED pin equals 13, and then if you go down here and say digital write LED pin, it'll look up into the variable, notice it says 13, and fill in the thing for you. So you can use variables to make things more readable, and that also helps later if you put this through a lot of code and you find you want to change the pin, instead of going through all your code and changing all the 13s to like, a 10 or something, you just go up here and change, one number to 10. So it's a little easier when you're trying to, update things like that. But anyway, we set 13 to high, so we are giving voltage to the LED to turn it on. Then we have a serial flush that just dumps the data. Then we write this high so we can take data in. Now this stuff is really confusing even to me. This is for the VT100 screen commands, which like PuTTY does. It emulates the screen. So this is the fancy code that it writes to make it display stuff. So he talks about it a little bit, but I don't really use it, so whatever. Just realize that all this stuff here is just sending commands to the PuTTY terminal window so they can write stuff, and then you can see the text that it prints, and it skips lines and all that crap. Now we have a delay of 3000, that's 3 seconds or 3000 milliseconds, and that just tells it to wait 3 seconds so you can actually read what's on the screen. And then it starts doing stuff. So it sets this low and blah, 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 waiting for data. So this right here is the loop. So this, I should have mentioned, the setup only runs once. So that's good for, initial startup things. And then after that, and then the loop runs continuously. So the things you put in the loop should be the main code. So it looks at the instructions and does everything, and then when it gets to the end, it starts right at the beginning and does it all again. All right. We have the first if statement. So an if statement looks to see if a statement is true, and if it is, it does the thing. If the thing is not true, it skips it. So if serial.available, so it's checking in the serial library. Right here, there's a serial library, and it writes commands. So instead of having to write all the code, you just find yourself a library where someone already did all the hard part, and then you just reference a command from that library to do. So serial.available, it checks to see if there is serial data available. And then it checks if serial.available is greater than 32, so it makes sure that it's read in, information, then do this stuff. So if this is true, then everything from this curly bracket onto this curly bracket, it will finish. So it sets the previous to the current, and then the current to serial.read. So it'll read in whatever the byte is and set that equal to, it'll set current equal to whatever it read. And then next is set to peak. Peak is a little different. It reads it without modifying it. If you read it, I think it takes it off the buffer, and peaking looks at it but keeps it there. So by doing this, we start with a 3-byte search. So now we come to our second if statement. If previous equals FFF or FF, which is 255, that would be our idle line, which is the ending bit. So if previous, which would be, when it switches this all around, if previous is set to 255 and current is set to 0, then we know that we found the end and the beginning. So if this and is like a comparator, so it's saying if this is true and this is true, then do. So if one of these is true but the other isn't, it won't happen. So then we come down to another if statement here. If the next one is not equal to 0, that's what this little exclamation mark means. If it's not equal to 0, then it starts reading in everything to the arrays. Now this kind of works, but sometimes it doesn't if this pattern shows up somewhere else. So if you get 255, 0, and then something that's not 0, it'll start reading and think it was in the beginning. For a week or two, I got stuck on this because it started grabbing from the wrong part of this from the stream, and I was getting weird data, and I just really couldn't figure it out until I looked into that. So on my version, I set this so that if it's equal to, notice if it's double equal. There's a difference between comparators and setting something equal to something. So if there's 2 equal signs, it's asking if it's equal to. If there's 1, it's setting it equal to. But anyway, it would check if it's equal to the program number, which on mine is 177, so I just type that in. Or if you want to keep the hex, you would modify this to B1. This 0x in front is telling you that the next number is hex, so this is a hexadecimal. If you just write, FF or 00, it's not going to know what to do with it. But anyway, as long as this condition is true, so it keeps searching through 3 bytes, 3 bytes, 3 bytes, and if it finally finds this, then it'll do the main code that actually puts everything into order. So it'll write the LED high so that you know that we're getting in good data, and then it does a for loop. So a for loop is you have like a beginning and a thing, and then the thing you want to do, or something like that. I forget exactly how it is, but look up for loops. They're very useful if you want to do a lot of things over and over again in a particular order. So if you got like a 1, a 2, a 3, a 4, and you want to do things in consecutive orders over and over again, this is useful for that. So the first for loop is it takes a position and checks if it is less than 31. If it is, then it adds to the position number so that it'll increase, and then the data stream position number is serial read. So this byte is read and put into this data stream array as the position. So at first it starts out as 0. So at the beginning of this for loop, it reads the data and puts it into number 1, or puts it into number 0. So then it goes through the code again and loops. So now we notice that it's 1, it does the thing, and now it reads the next byte and puts it in position 1. And then it'll do the thing. Now this is 2 because this right here is an addition. It adds 1 to this variable. So then it would be, 2, and then it goes down here, it reads, puts it into 2. It goes on, 4 on, and 4 on. So when this hits 31 or whatever, it's checking if this is less than 31. So if this is 31, then it won't do this anymore. The condition is not met, and we're done the for loop. So that's the first one. So we have this set for our data stream, and then we have average stream. So for average stream, it reads the same thing in, but it just averages it. So it reads it once, reads it twice, and then it divides it over here. So you get just a basic three stream average. Yeah. And then as long as that's all good, this will happen as long as this is less than 3. Once the loop is greater than 3, and then we're done this loop entirely. Then we write it low to show that we've read in all the data, and we'll write the 0 pin low, and we'll set the loop to 0, so that just resets everything. So now that we have all our data into arrays, now we can read them. So on his, this is all the old stuff, so this might not be the right order and all that crap. But yeah, now what he's doing is he's setting the streams equal to other variables, so they're easier to read and know what you're looking at. So instead of going, oh, I want to look at data stream 1, oh, I'd rather look at program version, which would reference data stream 0. Now we have a couple things. Stream, since this doesn't change, it's not useful as an average, as he said. It'll always be the same. So he's taking the first number. This is not ever averaged. It's just straight off the line, raw. Now if you come down here to the map sensor, this one is the average stream. So that's when it takes 3 of them and then divides it to get an average. So it's smoothed out. And he does some math in here. So the average stream multiplied by this number would equal the map. Now, these calculations are rough. He got them pretty close, but I was able to backprobe the snap-on scanner and get the exact numbers and all that. So now if you reference map, it'll look for the stream and do the math for you. So this is, by doing this, it's a lot cleaner. You don't mess up the streams by directly messing with them. You set it equal to another variable that stores all the calculated information. And then down here on RPM, he did some interesting work where I guess sometimes he got burpy data. So if RPM ever equaled 8,000, if it was greater than or equal to 8,000, it is set to 8,000. So if this read 12,000 for some reason, it would set it down to 8. Otherwise, it would just do this where it takes the two together and divides by the number and does all that crap, blah, blah, blah. And so on and so forth. So then, yeah, you can use these. So you reference this later in the code if you want to print that somewhere, and it does it. And then down here is all this complicated stuff that prints it all out onto the screen. So, yeah. So that's how his 3-byte search works, and all that. And then down here he put some stuff in here to see what he found. And I updated it in my code to represent what I found. So I'll just really quick, I know you're probably getting really tired of this crap and your brain's about to explode, but I'll just show you my version. So I have all mine updated and set up and everything's blah 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 blah. Okay, so I have 4 different arrays and they're read into the array, so we have a data order and it adds stuff and it displays that on the screen. So what I did is if you come up here, we have our data array, so each thing is in an order. So we have display map, CTS, IAT, all that. So what happens is when you push a button, it just goes to the next one, and the next one, and the next one, and the next one. And I have 4 separate orders, so it looks through this 4 times and does all that. So there's a lot of other crap in here. You could look through the code. I have a lot of it commented, so I don't know the proper formatting and all that, so I just did it the way that I thought was the most readable, but it prints it all out to LCD screens, and there's a lot of crap. But yeah, there's a lot in here, a whole lot. So here's my updated version and all that crap. But yeah. All right. Well, that should get you going for the most part, so you can kind of understand what's happening, and you can read in some data, and you can write your own code. I forgot to add that if you do want to do this and read it on an LCD screen instead of your computer, so you want it more portable, this is what I initially used. It's an LCD keypad shield. This is just a generic, $3 part off eBay. You can find them everywhere. It's got a screen in here, it's got buttons in here, and just all kinds of stuff. It's really cool, and it's cheap, and it just works. So that's the other cool thing about the Uno, since it's a standard form factor. You can just take this guy, and it's got pins in here. You line them all up, and snap it in, and boom. Now you have your shield set up. And this one actually has holes in it, so you can put your wires into these. So you can put your 5-volt here, and you can put your RX pin over here, and all that crap. Yeah, if you just want to get started real quick, put it all together, and See if you read anything. That'd be great. Now, if you do this, please, please, please tell me that you did it. Okay, and tell me if it worked. And if it did work, tell me the year of your truck. Tell me what kind it is, if it's a Cherokee or a Wrangler or whatever. Tell me what kind of engine you have, if it's the 4.0, the 2.5, or the 4.2. And let me know what kind of trans you have, if you have an automatic transmission or a manual transmission. I don't know if this works on manual, so if it does, please let me know, because I got to do some alpha testing. I'm going to send some models out to some people and see if it works on their truck, and then also ask them for feedback about the design of things, you know, the menus, the layouts, how things feel, hardware, software, all that. I need, you know, stuff on all that. So, all right. Well, best of luck out there, and I'm sorry if your brains are broken. Who knows, I might have something a little simpler next week. We'll see. This project has eaten so much time, I haven't been able to work on the Jeep, so once this is done and rolling, I'll be able to do some more stuff on that. So, as always, you know, stay tuned.